Hello everyone, you are welcome to this channel. Today we shall be doing further study on isothermal reactor design using rate data. Often in the industry, there is a need to upscale or to increase production. Maybe it is being run on the batch reactor before, but in order to meet demand and market need, we need to upgrade to continuous flow reactor. So to do this effectively as a chemical engineer, we have to obtain the rate data, often from the batch process, and use it to design the continuous flow reactor. So let's look at this typical operation in the industry. Paracetamol is produced by the acetylation of aminophenol with acetic anhydride. The reaction is shown on the screen. So let's assume the pharmaceutical company is desiring to scale up the production from batch to continuous state tank reactor. So as a chemical engineer, you are required to design the volume of the reactor needed to achieve the desired goal. So this will require that we have some batch data or the reactor data or reaction data from batch reaction. So in order to design the CSTR, we need this batch data. The time and how the reaction is consuming the key reactant, which is like p-aminophenol here. So we were given the initial concentration of the acetic anhydride as well. So we are given the initial concentration of the acetic anhydride. So we can see that it is very large. It is very large. 20 mole per dm³ compared to the initial concentration of the p-aminophenol, which is 2. So it's like 10 times the initial concentration. So B is very large compared to A. So, and the implication is that in reaction engineering, we can assume that B is constant throughout the reaction because it is very large. So CB equals to CB naught. It's like it's not changing much. So in order to perform the design for CSTR, we need the rate data. And what is the rate data? We talk about minus RA equals to KCACB. These are the two reactants. We have two reactants here, CA and B. So rate of reaction is dependent on the two, and we don't know the order. This one may be alpha order and this one may be beta order. But the analysis we are doing here says that what? Determine the reaction constant Ka and reaction order in A, alpha. Use graphical method. And there is an assumption here. Assume that it is first order reaction in B. So we have our minus RA equals to KCA alpha or KACA alpha, and CB is 1 now because we have been told to assume it. We have been told to assume that. So the first task is to know that now that we have CB is equal to CB naught because it's constant or almost constant, therefore we can have, and our K is also constant, therefore we can now say K prime is C alpha. So our K prime means what? Ka CB, which is CB naught as well. So please note that. So because these two are constant now, we can just simplify our rate expression like that. So in order to now estimate our K and alpha, we need to, first of all, remember the data here is from batch. So we need to invite or to recall the batch design equation, which is dNA dt equals to RAV. So we also assume that our V is constant. Therefore, we can get our concentration data. C is equal to NaV. We believe that the V is not changing much, which is reasonable in liquid and isothermal condition. So let's substitute this for array and simplify, so we can have the Ca, that's Na divided by V. The Ca dt, Na divided by V give us Ca is equal to, then substitute for array, which is now minus k prime Ca alpha. Remember, I've told you our K prime is now KACB, since both of them are constant. So we'll use it to simplify in order to get our alpha out first. So having done this, the next, in order to linearize this expression, we can have it like this: minus the Ca dt equals to K prime Ca alpha. I try to rearrange the negative sign. Then let's linearize. Take the ln for the 2. So take the natural logarithm of the 2. So we can have ln minus dCa dt equals to ln K prime ln K prime plus alpha ln Ca. So if you can evaluate this expression, when we plot ln minus the Ca dt against ln Ca, that means our slope of the graph will be alpha and our intercept will be ln K prime. So that is the simple thing. So the task now is to get our dCa dt. We don't have the Ca dt, we only have Ca and T. So how do we get our dCa dt? That's the first task. The second task is to, I think that's a major task now. That's a major. So how do we get our dCa dt? So to get the Ca dt, there are different ways we can evaluate that. We can either use graphical method, we can use a finite difference, and we can even use polynomial. But in this tutorial, I will just be using graphical method. I'll be using graphical method. So there are 2 steps I'm going to take to get there are some steps I'm going to take to get the Ca dt. To get the Ca dt, we can have what is called the differencing method. Differencing method. So the differencing method states that it goes like this: T is equal to 0, 15. Those are the T values we get: 30, 60, then we have 120, then we have 240. And we have our Ca in mole per dmq. We have our Ca as 2, 1.35, 1, 0.65, 0.35, and 0.1. So we have to now get our differencing, which is what? Delta Ca, delta T. Delta Ca, delta T. So simply put, we say delta Ca, delta T means Ca2 minus Ca1, Ca2 minus Ca1 all over Ta2 minus Ta1. T1, T2 minus T1. There's no Ta. T2 minus T1. So in this case, we have Ca2 for these two, for this and this. That will be 1.35 minus 2 all over 15 minus 0. So that's going to give us negative minus 0.0433. 0.0433. 4.33 minus. So in order not to be having this decimal number, to make it more presentable, so we can multiply whatever we are getting by minus 100 so that it will give us a bigger number, and it also eliminates the negative. So let's have something like this. So it's going to be minus delta CA delta T multiplied by 100. So that's going to give us a meter number 4.33. Remember, we have multiplied by 100, so we need to divide it at the end of the day. 2.33, 1.667, so 0.5 and 0.20833. So our T is still there as 0, 15, 30, 60, 120, and 240. So what this means is that, and we have our CA as well as normal. So what this actually means is that this delta CA means between 0 and 15, we have 4.33. Between 15 and 30, we have 2.33. And between, so let's me if we put it at 0 to 15 is this. That's T range now. Then this is 15 to 30. This is 30 to 60. This is 60 to 120. This is 120 to 240. So that is the differencing result. So we are going to plot this differencing result, and we are going to obtain a kind of histogram where we are going to evaluate our dCA dt. So let's see how this can be achieved. So I try to pop up this electronic graph, and the way I'm going to do it is to we can say we are going to plot minus the CA dt by 100 against our T, So you remember T is from 0 to, from 0 to 240, and this one is from 0.2 to 4. So we need to divide it reasonably in order to get the best of results. So along the y-axis, so this is minus delta CA delta T times 100 times 100 or times 10 to the power 2, and this is T in minute. So let's start from here. Let's say this is our 0 point because of the shortness of this electronic graph. So we are going to, so let's make it 40-40. So this is going to be 40, 80, because it's a short graph in width. So that's why I'm using this. Otherwise, it should have been 30-30, which will be more better. So 120, 160, this is 200, and this is 240. So let me pick a bigger. Okay. So along the y-axis, so since it's between, the value is between 0.2 to 4 point something. So I would rather want it to be like 0.5 for every 2 boxes. So it's going to be 0.5. Then this is going to be 1. This is going to be 1.5. This is going to be 2, 2.5, 3, 3.5, 4, 4.5 here. 4.5 here. So though this is 2, but I think we can manage this. So now let's plot the graph. So we are going to plot 4.33 between 0 and 15. Remember, we are plotting histogram. So 0 and 15, I'm going to plot 4.33. So this is, remember, this is so this is 30 point. The point 30 is here, so that means this point 15 is around half of it, which is here. So 4.3, this is 4.1, 4.2, 4.3. So 4.1, 0.2, 0.3. So I'm going to just, so this is 4.3. Sorry, it's not very straight. So this is 4.3. Sorry, let me. So don't mind the zigzag. So the touch pen is not very stable. So the second plot, so that is the first histogram. The second one is between 15 and 30. I'm going to plot 2.33. So 15 and 30. So this is, remember, this is 30 points. So that means between, so I'm going to plot 2.3 is between here. So then the next point is, sorry, the graph is not very smooth, so, and I can't help it for now. Then the next point is 30 to 60, 1.667. So 30 to 60, 1.667, 1.5, 1.6 around there. That's 30 to 60. So around here, 30 to 60, sorry. So just try to get the idea, because it's not very smooth on this electronic graph. Then from 60 to 120, we have 0.5. So 0.5, 0.5, 60 to 120. I think this is better. Then from 120 to 240, we have 0.2. So we have 0.2. 0.2 is around here from to 240. So you can see how the histogram looks like. So though the starting point is too congested. So having done that, we are going to draw a smooth curve to cut the middle, to cut through the middle of all the histogram chart. So to cut through the middle, 1, 2, 3, something like that, 1, 2. So around here. So we are going to, okay, sorry, this is the, this is 240 point, not that point. So this is the 240 point. So that means the center is around here. So this is the center here, the center here. So you try to cut. So then we draw a smooth curve. Don't mind the drawing here. I also have it on. To draw a smooth curve, then here, here, and so on. So that's a smooth curve we have used to join the center of each histogram bar chart. So and we extend it beyond the first histogram to cut the y-axis here, and we extend it at the end too to cut the last axis. So having done that, wherever the curve now cut the, like here now, I think it's clearer here. So here we need to pick the point to be the corresponding point for 120. We need to pick the one for 15, the starting point, the 30, the 60, where the curve cut all the histogram chart. So we need to get all those to be corresponding to the time we have. So from the data I have here, I actually pick those points. So this is the differencing point, and the data I have here shows that the cutting point is, that is the dCAdt. These are the value. So when we still multiply by 100, so minus dCAdt multiplied by 100 give us at 0.15, at 0.0 rather. So we have it at 5.3. That is at this point where the curve cut the x-axis, the y-axis. So we have it as 5.3. At 0.15 of time, we have it as 3.5, 1.9, 0.95, 0.45, 0.05. So those are the dCAdt. So those are the dCAdt point. So now that we have the dCAdt point, so that means we have t, which is 0, 15, 30, 60, 120, and 240. And we have our CA, you remember that. And we have now our minor delta CAdt, delta t times 100 multiplied by 100. Then we now, from there, we have our minor dCAdt times 100. And those points are what? 5.3, 3.5, 1.9, 0.95, 0.45, 0.05. If you try it on your own, you are going to get approximately the same thing. So the next task is to now, if you remember where we started from, we want to plot minor DC. We want to plot minor DCA, lane minor DCA against lane CA in order to get our slope as alpha and to get our intercept as lane K prime. So that means we need to create a graph of lane minor DCA dt. We need to create a column for that, as well as so we need to find lane minor dCA dt times 100. We need to create a graph for that. Then we need to create lane CA as well in order to get. So we may not find the lane and simply plot on log graph, but since majority of the students don't have the log graph, I think it's better we evaluate this. When we evaluate this, like the evaluation I have here, I have already divided by my 100, so I don't put the 100 again. So that's minor dCA dt alone. So I divided all the values I get from here. All this dCA dt I divided by 100. So we are now having 0.053. So before I find the lane, so the result is here. So this is what you are seeing here on the screen. Minus the CA dt, so divided by 100. So I remove the 100 and evaluate only the CA. So I divide by all through by 100. Sorry, I'm talking of this point. So I divide through by 100 in order to get only the CA dt. So and the result is here. So for the first one is minus 2.3, so that when I find lane 0.053, I got this. Lane 0.035, I got this. So, and so on and so forth. So I've removed the 100 from the heading. So similarly, I find my lane CA as well, giving me all of this, based on the original CA data that was supplied to us. So with that, I can now plot on my ordinary graph. So I can plot the value here against the value of lane CA. So when I did that, I got this. Plot. And this plot shows, then I find the trend line in Excel. You know how to find the trend line in Excel? Just say format axis, and you can always insert the trend line somewhere here. So then you can also model it rather. So I think add trend line, add trend line. So this is how to add trend lines. This is a trend line that I've selected. So it gave me this equation, mine 1.562. So why that is, what this is saying is that y equals to 1.562 1x minus 3.926. That is lane minus the CADT is equal to lane alpha lane CA plus lane K prime. So that means my alpha is 1.56. So alpha is equal to 1.562. So approximately the order of the reaction is equal to 1.5 or 1.6. So then to get our K lane K prime equals to minus, that is, this value represents lane K prime now, is equal to minus 3.926, and our K prime is equal to exponential of that, which is equal to 0.0197. So now, if you remember very well, we got our K from a combination of parameters. If you remember very well, we got our K, where we say our K prime equals to what? KACB. So our K prime equals to KACB. So K prime equals to KACB. So our CB has been put at first order. So if you remember that, that means this is equal to KACB. Our CB is not changing. You remember it's equals to CB naught, which is this 20. Therefore, we can now say 0.0197 equals to KA times 20, and our KA equals to, when we evaluate that, our KA is going to give us 9.86 times 10 raised to power minus 4 dm³ per mole square per minute. So always remember the unit. So now dm³ per mole, everything square, and everything per minute. So having done that, that means our rate expression is now equals to minus RA equals to 9.86 times 10 raised to power minus 4, then multiply by CA, which is 1.5 order of reaction, and CB, which is first order of reaction. Now, in the industry, we have now evaluated our rate data, so we can now go ahead to design our industrial reactor of CSTR. So the company decided to produce 1 million grams of paracetamol per year, that is 365 days in 24 hours. 1 mole per dm cube solution of A is constantly fed to the reactor. Equal concentration of B is also fed into the reactor. Determine the volume of CSTR needed. Determine the volume of CSTR needed. So the company is looking for to produce C. You remember our C is our paracetamol C here. So we want to produce C, which is the paracetamol at 1 million gram every year. So you remember our rate data is given a minute. Remember that our rate data is given a minute. Therefore, we need to find how much are they going to be producing a minute. So that's their target of 1 million, but how much would it translate to in every minute? So let's see. So the molar flow for the this thing can be converted from 1 million gram 10 raised to the power 6 gram per year. We want to convert it to minutes now, and we have to convert it into mole too. It's given in million grams. We need to convert it to mole too. So that means we need the molar mass of the paracetamol. So 1 million gram per year is going to flow, and remember 1 year has 365 days, and one day has 24 hours, and 1 hour has 60 minutes. So this is where we are going, minutes. So if you are going to second, that means we have to go into once what is it called, 1 minute into second. But because we are stopping at minute, so that is where we are going to stop it. Then how do we convert this gram into mole too? So remember 1 mole multiplied by 1 mole having 151.1 gram. If you sum the masses of the paracetamol component, we are going to have that. So when we evaluate this, our molar flow for the paracetamol will be 0.01259 mole per minute every minute. That is what the company should be producing. So how do we now make use of this data? How do we make use of this data? We have to calculate the p-aminophenol that is going to be needed to meet this. So you remember our FC, which is paracetamol, is equal to Fa naught p-aminophenol multiplied by the conversion of that p-aminophenol. So we can use that equation to now get our molar flow for the p-aminophenol, which is Fc over Xa, which is equal to, we have gotten our Fc per minute, so it's now equal to 0.01259 divided by 0.95, which is our conversion. Then the conversion was given in the question. That is 95% conversion. So note this, 95% conversion. So that means our continuation of the last tutorial. So we have now gotten our Fa naught. We got our Fc, the molar flow for paracetamol in mole per minute, and we can now get our molar flow for the reactant p-aminophenol, which is going to which is evaluated to be 0.01325 mole per minute. So once we get this, the next thing, so that makes our work very easy, and what we need to do now is to get our volume of CSTR. Remember, the volume is equal to Fa naught X divided by minus Ra. So all these parameters we already gotten. So we have Fa naught is equal to 0.01325 multiplied by the conversion 0.95 divided by the K, this is KCA 1.5 CB, which is equal to CB naught. So when we evaluate that, we are going to have 0.01325 multiplied by 0.95 divided by 9.86 exponential minus 4 multiplied by CA naught. CA is equal to CA naught 1 minus XA 1 minus XA raised to power 1.5, then CB, which is equal to CB naught. Which is equal to CB naught. So when we evaluate this, CA naught is already known to be 1, and 1 minus this XA is 0.95. 1 minus 0.95, that is 0.05 raised to power 1.5. So when we evaluate this, our V or volume for CSTR will give us 57.09 dm cube. So that is how to evaluate our continuous flow data based on batch data, which we use to estimate the rate data. Always take note of this. We are unable to directly evaluate our differential term because we don't know the order of reaction. We don't know if we have known the order of reaction, let's assume it is 1. That means CA will just come under here and will become it will become, so as if we have minus the CA dt equals to is equal to K prime CA. So since we put this as 1, that is our order of reaction for CA is 1, therefore we don't need to go to the trouble of looking for graphical method to evaluate anything. So it will just become K prime dt here. So and this one will give us minus ln CA is equal to K prime T plus C, and we can easily evaluate this. But because we have alpha here, so which we don't know the value of, that's why we have to be careful in separating as we did, that is minus the CA dt equals to K prime CA alpha. We don't know alpha. That's what led us here. So that's why we have to linearize like this. The CA dt equals to ln K prime plus alpha ln CA. So because we are not sure of the value of alpha, so we cannot integrate it under the CA. That's what led to all the routes we have followed in order to obtain our rate data, finally design our CSTR. I believe you enjoyed this lecture, and any comment, any observation, or any question can just be posted below. Thank you so much for listening.